Federico, take it away in the past, it turns out.
Hello everyone, thank you for coming to our talk on synthesis in Uclid5. My name is Federico Mora, and I'll be presenting this work done with Kevin Cheang, Elizabeth Polgreen, and Sanjit Seshia. So the main motivation for this work is really that verification takes a lot of time and effort. For example, verifying SGX and Sanctum took 4 months of modeling work. So even though the actual checking of the verification, running the solver, is reasonably quick, we have to do a lot of things like strengthen variance, annotate functions with pre and post conditions, and model system calls in the environment just to get it to a state where the solver can execute quickly. Luckily, however, tasks like these can be automated using Cygus. So in this work, we set out to use Cygus solvers to unify synthesis for verification tasks in a clean way inside of Uclid5. More specifically, we contribute 2 main things in this work. First, we describe our integration of synthesis into Uclid5, and second, we use our new integration to generate a set of Cygus benchmarks that we think will be interesting to the community. One of the things that we're particularly excited about with our new integration is that it is very flexible. So users can define functions to synthesize and use them anywhere in their code for any verification technique and any kind of specification. This integration really is only possible because of existing Cygus engines. So what we do here is we develop a scheme to be able to reuse our verification encodings to produce Cygus queries that existing Cygus engines can handle. Okay, so there is a lot of related work in this space. For example, for the 3 use cases that we mentioned before, there is a plethora of papers that have interesting techniques for dealing with them. Here we highlight 3. Beyond these 3 use cases, there's a lot of related work like program sketching, which lets users leave holes in their code, and will get the solver to fill those holes in for the user automatically. There's program repair, which often uses program sketching and is quite related to how we generate our benchmarks. And of course, there are verification engines with synthesis capabilities. So this includes stuff like Rosette and Uclid5's old synthesis integration. The thing that sets the new integration apart from all of this is that we give users a very generic input format that they can do any of these things, and we will generate queries for existing Cygus engines to handle. Okay, so before going under the hood and seeing how this is all actually implemented, let's look at an example of how a Uclid5 user would actually use synthesis. Okay, so suppose that we wanted to model a Fibonacci sequence in Euclid, and then we wanted to prove a property like that the sequence is always increasing by induction. The way we would do that is first we would describe our system. So here we have 2 variables, a and b. The initial value of a is set to 0, the initial value of b is set to 1, and we define a transition relation. So in this case, the new value of a is set to the old value of b, and the new value of b is set to the old value of a plus b. Then we want to state the property that we actually want to prove. So in this case, we want to prove that a is always less than or equal to b, which would imply that the sequence is always increasing. Finally, we have to tell Euclid how we want to go about proving this specification about this system. Here we're telling Euclid to use induction. Okay, so the induction algorithm is going to check 2 things. First, it's going to check that the property holds at initialization. And second, it's going to check that if the property holds on entry to the transition, then it will hold on exit. In this case, the property actually does hold, but it is not inductive. So P2 is going to fail. We're going to find a counterexample to that. And the Euclid user would need to manually go back and strengthen the invariant. With synthesis, the user can actually ask Euclid to strengthen the invariant for them. Here, the user declares a function to synthesize called h, and then conjuncts a call to this function at the end of the invariant to get Euclid to strengthen it and make it inductive. One possible answer that Euclid might give is a function body for h that returns true if and only if its first argument is greater than or equal to 0. This will make the invariant inductive and will make the proof pass by induction. In that example, the user used a function to synthesize to strengthen an invariant, but really they could have used that function anywhere in their code, and instead of use induction, they could have used bounded model checking or anything like that. So now we're going to talk about how we achieve this flexibility inside of Euclid. So synthesis in Euclid follows a pretty simple workflow. We have a front end that does the parsing, then we have a symbolic simulator, which you can think of as actually generating the verification conditions. What we add is this new interface that communicates with the symbolic simulator and is somehow halfway between an SMTlib interface and a Cygus if interface. This is really useful because if there are no functions to synthesize, we can use this interface to spit out SMTlib queries. And if there are functions to synthesize, we can spit out Cygus if queries. The best thing about this is that our verification algorithms are completely untouched. And whenever we add, a new proof procedure or a new technique, we will get synthesis for it for free. Okay, so let's focus in on the relationship between our new intermediate representation and the SMTlib interface. Okay, so suppose that we had the same model from before, the Fibonacci sequence in Euclid, but instead of asking Euclid to find a function that will strengthen the invariant appropriately, we're just giving Euclid the answer right away. So here you see that instead of the synthesis function declaration, we have a function definition, and we're conjuncting it in the same way. Euclid will generate something like this SMTlib query, which is a little bit messy, but what's important is that it's just looking for a counterexample to verification. Specifically, it's going to be unsatisfiable if and only if there are no counterexamples. So if we can't find some values for A and B that violate either the initial condition or the inductive step. With a synthesis function declaration, Euclid will basically generate the same query. So here what we see is the syntlib encoding instead of the SMTlib encoding, and you'll notice that it's almost exactly the same. In fact, the only difference is that we have this funky synth blocking fun command. The semantics of this query is essentially, does there exist some function h that will block all models for the underlying SMTlib query? In other words, does there exist a function h that makes the verification pass? Because the syntlib interface and the SMTlib interface are so similar, whenever there are no functions to synthesize in the Euclid models, we can actually just directly go to SMTlib. In other words, the syntlib interface and the SMTlib interface are the exact same. When there are functions to synthesize, we need to do a little bit more work to generate a Cygus if query that existing engines can solve for. Specifically, we need to go from the kind of queries that the syntlib interface deals with to the kind of queries that the Cygus if interface can handle. And this isn't very hard. So the main difference is that the syntlib interface is trying to find a function that blocks all counterexamples, where the Cygus interface is trying to find a function that works for all inputs. From a syntactic perspective, all we have to do is perform these 4 transformations, the first one being the most important, which essentially translates assertions into negated constraints. Going back to our running example, here is the syntlib encoding as we saw before. And here is the SYGUS if encoding. So as you can see, we just changed a couple of definitions, negated the constraint, and we automatically have a query that we can feed into a SYGUS engine and get an answer from. So we implemented everything, and our code is available online. And with that in place, what we began to do is construct benchmarks. So we actually built 25 individual benchmarks. And just to give you a taste of what they're like, I'm going to go over 2 examples. The first example comes from a CAF 2020 paper, Verification of Quantitative Hyperproperties Using Trace Enumeration Relations. So this paper had accompanying Euclid models that we grabbed and transformed to create some of our synthesis queries. This particular model uses a function definition at the top, pi balance, that is then called inside of the init block inside of 2 separate assumed statements. To generate one synthesis query, what we do is we replace that function definition with a synthesis function declaration. This basically means that we're asking Euclid to find that function for us. The second example comes from the Uclid tutorial. So this is a model that defines a traffic light system. To construct the benchmark, what we did is we identified a part of the code that we wanted to replace, and then we declared a function to synthesize and used it in place of the existing code. The more interesting thing about this benchmark is that it uses linear temporal logic specifications, and it uses bounded model checking, in this case unrolling 10 times, to check those specifications. So I wanted to highlight this because it really shows that these functions to synthesize can go anywhere in the code. They can be used for any kind of specification that Euclid supports, and the user never has to think about it. So to wrap up, we observed that verification takes a lot of time and effort, but that luckily SYGUS can be used to automate a lot of this work. We then talked about how Uclid5 now uses SYGUS to actually do this by letting users define functions to synthesize and use them anywhere in their code for any verification technique for any kind of specification. Unfortunately, we found that when generating these benchmarks, we would very quickly run up against the limits of the state-of-the-art synthesis engines. The good news is that means there's a lot of work left to be done. So we want to work on optimizing things on our end and generate better synthesis queries from Euclid. But we're also releasing the benchmarks to the public as is right now because we think that they might be valuable for people working on improving the solvers themselves in the meantime. So thank you for coming to our talk. Please check out our paper on arXiv, our code, and the benchmarks on GitHub. And if you have any questions, I'd be more than happy to answer them now.
All right, let's go ahead and thank the speaker. Virtually, but Federico and Elizabeth are actually here for questions. So go ahead and post your questions on Slido. I'll give that like 5 seconds or so because they kind of fly in afterwards. We'll just jump right into it. Federico, Elizabeth, are you both there?
Yeah.
Excellent. Double excellent. Okay, cool. All right, so let's go ahead and jump into it. First question, what are the practical limits of your system handling any kind of specification or synthesis style?
So we're being a bit mean to SYGUS engines, and we're actually putting a lot of the onus on them. So the performance of our system really depends on the performance of the engines that are actually solving our queries. Right now, like I mentioned at the end of the talk here, we're finding that we're kind of pushing the limits there reasonably quickly. There are a lot of cases, like the examples that I showed, the running example, for example, we solve instantly. But as things get more complicated, we're having a bit of a harder time, which is part of the motivation for releasing those benchmarks.
Okay, since you mentioned the pushing the limits thing, there's a question about that. I'm going to jump that one to the top of the queue. Could you talk more about how you're pushing the limits with respect to SYGUS, and then what that actually looked like, and any plans or thoughts you have about that based off of your experiences?
So what I mean by pushing the limits, I mean pushing the limits of the performance of the engines. So we're finding that we're timing out on some queries that we think, you know, it's reasonable to aim for to solve these in like a next iteration of a tool. That's kind of what we're going for. We're not pushing limits of like expressibility or, you know, the syntactic capabilities or anything like that. It's performance that I'm talking about.
All right, excellent. Is that as a follow-up to that, I guess, because I'm curious, is that something your tool would then handle, or is that something you're pushing onto other SYGA solvers to eventually fix in the future?
So I think there's a lot of stuff that we can do on our end, and there's definitely things that we're planning to do. You know, right now we're generating the queries in a rather simple way, but I think there's a lot of optimizations and pre-processing that we can do before asking the engine. We're also looking into you know, the engines themselves, but I think it'll be work on both sides that makes it work.
Excellent. All right, new question from Anonymous. How do you determine the grammar that is used in SYGAs for your problems?
Yeah, so this isn't fully implemented yet, so I didn't put it into the slides, but this synthesis function declaration should be able to take in a grammar. So right now we're just using kind of the default grammars that you know, SYGAs engines will come up with, which Nicholas talked about. But we do want to be able to support more flexibility in terms of the grammars, and that's on its way.
All right, excellent. I'm happy all our talks lined up, huh? That was a nice throwback there. Haniel Barbosa asks, what SYGA solvers did you evaluate? And if we have any other questions, please post them in Slido. That was the last one I got in the queue.
So the one that we've been having the most success with is actually CVC4. We've also tried stuff like EU solver, and I think actually we've gone through, you know, the recent competitions and tried most of them. For most of our tests, we actually rely on CVC4 because we've been quite happy with its performance.
Okay. Daniel Barbosa with the follow-up to the last second. Incredible. What timeout did you use? Did you try other than the default options?
So I have this written down somewhere. I can't think of it off the top of my head. I think, you know, in many cases, the timeout was we were, you know, losing patience more than a physical, like, you know, 20 seconds or something like that. But it was like I would set it and go to lunch or something like that. So yeah, so I can look up the details, but it's I don't know if I have like a specific, you know, this many seconds answer to it.
Okay, cool. Queue is empty, but I'll ask sort of one last question I had. Oh, nope, someone won. Anonymous asks, is the grammar for a function to be synthesized dependent of where the function is used? Is the current default only type dependent?
That's very interesting. So we haven't explored anything about like, you know, changing the grammar depending on how it's used. So right now we're really just using the default grammar for everything. But that's a cool thing to think about. Yeah, maybe that's worth diving into. See if we can get better performance by having a grammar dependent on how the user actually tried to use the function. That's really cool.
Okay. Cool. And then Daniel Barbosa with the 3 at bat here. Regarding CVC4, the default grammar is only type-based. That's more of a comment. Cool. So I think that's all we got. Let's go ahead and thank Federico and Elizabeth for great work. There we go. Sweet. So I think that ends the Berkeley session. Thanks for everyone for listening in. Hope you all are inspired and to check out all this great work. The papers are online. I'll let Ravi take it away for our transition to break rooms.